Welcome to Linear Algebra. Glad you're here. We're going to start by talking about the very beginnings of the ideas. We'll see today matrices and systems of linear equations. As we talk about all this theory and numbers and matrices, and we'll get pretty heavy into the abstract ideas, I want you to remember, I put this picture of a piece of ancient pottery to remind us that these ideas have real applications and really powerful applications. One of my favorite applications that we'll see a little bit later in the course is being able to, at an archaeological site, using linear algebra, they were able to sort of order the graves chronologically based on pottery remains and using a lot of ideas from linear algebra. It's one of my favorite examples that we'll see in this course. Okay, a good question to start with is the question, well, where did linear algebra even start? Why do we talk about all these matrices, all these systems of equations that we'll see? So where did linear algebra start? It got its start by trying to solve equations that look like this, but not just one equation, a series of equations at the same time. So taken one at a time, each of these is a linear equation. But when we group them and we want to find out where all of them could be true at the same time, then it's a system of equations. A system of linear equations. In this course, we only talk about linear equations. So when we talk about systems of equations, it's systems of linear equations. And when we have multiple equations, we want to know an x and a y that will, or maybe there's more than one, that would make both of these statements true. And maybe it doesn't even exist at all, but that's where our hunt begins. We want to be able to find solutions that make both of those statements true. In this case, I'm going to give you the answer first. We haven't even talked about how to solve it. But say that we let x equal 2 and y equal, no, let's go the other way. Let's let x equal 3 and y equal 2. So I'm going to tell you right off the bat, this is the solution to this system. And why is it a solution? Because as soon as we take the first equation and we put in these numbers for x and y, we get 3 plus 2 equals 5. Yeah, that works for the first equation. The second equation, plug in the same numbers, 2 times 3 minus 2, let's see, that's 6 minus 2, definitely equals 4. So these two numbers work for both equations. And so we'll often write the solution to this system as, so the solution to the system, which we're looking for, in this case, we write as the ordered pair 3, 2. Now we're going to get a graphical look of this system of equations. We've got the first equation right here, and the 2x minus y equals 4. The second equation right here. And when we graph them, this is what they look like. There's our x plus y equals 5 line, and this is our 2x minus y equals 4 line, and they intersect right at the point 3, 2. So this, graphically, we can see that this point 3, 2 is lying on both of those lines. Here we've got two other linear equations, so we're going to look at this system of linear equations. And a good question to ask is, what makes an equation a linear equation? Well, the variables have no power. The power on the variables is all 1, and this is a linear equation in 2 variables. So we have 2 equations in these 2 variables that are both linear. Okay, when we graph this system, we get a picture that looks like this. There's our first line, it's negative 2x plus y equals 3, and here's what the second line looks like. These two lines are parallel, they'll never cross. there will never be a point in common to both of them. So this system of equations actually has no solution. We see it graphically, and later on we'll see algebraically how we would know that would be true. The third example of a system that I want to look at is this one. We have these, again, two different linear equations, and when we graph these ones, this is what it looks like. The first equation is this line right here. It intersects the y-axis at -3, intersects the x-axis, it looks like at 1.5. And then when we go ahead and graph the second equation, this is what we get. So we graphed it, you can't see it because it's lying underneath this line. These are actually the exact same line, they're expressed a little differently, but this is essentially the same line. If we took off this one, you would see that that red line is sitting right there also. So this is a system which has an infinite number of solutions because every point on the line is a point of intersection. Every point on the line works for both equations. So we just saw 3 possibilities for solutions. When we graphed this system right here, and plus we already knew, we get that there is one solution. So a unique solution. When we graphed this one, what we got were parallel lines. And so here we had no solution. There was no point where these two lines intersected. And the last one we graphed, it was those black and red lines. This system, they coincided everywhere. So this was a system with many solutions. And in fact, it had infinitely many solutions. One thing I'll emphasize right here is these are the only 3 possibilities for solutions to a system of linear equations. There is no way to get exactly, for example, exactly 5 solutions to a system of equations. You're either going to have one solution, no solution, or many solutions. And we'll see this time and time again. These are the 3 cases. We're going to spend a lot of time looking for solutions, and these are the only 3 things that will happen. The real power of linear algebra comes about as we move into larger dimensions, and so we're definitely not always in 2 dimensions, just an x and a y, and we want to look and see what happens as we move into larger dimensions. And we'll start by looking at 3 variables in 3 dimensions, and these we can still visualize. When we move into a 4th dimension, that gets harder and impossible after that. This is a system of 3 equations in 3 variables. We'll start using x1, x2, x3, and more than that, x4, x5, x6, etc. Just because theoretically, you can talk about a system of 27 variables, 27 equations, so you would run out of letters of the alphabet. So this is how we'll start doing our variables. And the solution to this system is x1 equals -1, x2 equals 1, and x3 equals 2. And we'll write it as an ordered triplet like this. So we think to ourselves, is this really right? Let's go check. If we plug these variables in these numbers in for the variables, it should check out for each of these. So -1 plus 1 is 0, plus 2 is 2, that one works. 2 times -1 is -2, plus 3 times 1, so that's 1. Plus 2 is 3, that one works. -1 minus 1 is a -2. Minus 2 times 2 is a -4, so -2 minus 4 is -6. They all work. So this is the ordered triplet that works for this system. So we'll try to visualize what this solution might look like in 3-dimensional space. And so if x1 equals -1, that's about right here. And then x2 equals 1, go that far on the x2 axis, and then up 2 on the x3 axis. So our solution point, -1, 1, 2, is right here. And what this represents is an intersection of 3 different planes. So it might look something like this, and maybe the other plane looks something like this. And then we could have a third plane looking something like this, and the only point that they intersect at happens to be this one right here. So it's getting harder to visualize in 3 variables, but it's still possible. Even in 3 variables, you only have 3 possibilities for solutions. You could have a unique solution where you just have one ordered triplet that works, and that's what we got right here. You could have a case where there's no solution to a system of 3 variables in 3 equations, and that might look something like, you get these planes that are actually parallel planes that never intersect, so there would be no point in common. And then again, you might have a situation where there are many solutions to the system. It could end up being that all 3 of them are really the same plane, or things get more interesting in 3 dimensions where you could have some planes maybe intersecting at one line, so there's infinitely many places where they intersect, but they're not the same plane. So we've got our 3 possibilities: unique solution, no solution, or many solutions. So from here we grow into larger dimensions, and we may be in 4, 5, up to n variables. And so visualizing becomes really impossible or very complex at the easiest. So as n, the number of dimensions that we're in, becomes larger, we rely on algebra a lot more than geometry, and so we emphasize this. We're going to actually solve our first system now, and to solve systems of linear equations in n variables, we'll use a combination of matrices and elementary row operations and a method called Gauss-Jordan elimination. Okay, here it is. Here's our system that we're going to solve, and it looks like we're in 3 variables. We've got 3 equations. The first thing we're going to do is put the important information in a matrix. This is what a matrix looks like. It's just these square brackets, and inside we're going to enter the coefficients of each of the variables and also the constant term. So it's a rectangular array of numbers, and we drop the variables, but just by the position in the matrix we know which each one represents. So the first entry we'll make is 1, and that comes from the implied 1 coefficient on x1 right here. The next entry will be -2, and then 4, and then 12, and that will make up our top row. So -2, 4, and 12. So you just write the numbers, you keep spaces in between them so they're different numbers and not, for example, -24, and then you move on to the next row. The next row should be 2, -1, 5, 18. And so we've got 2, -1, 5, 18. And the third row will be -1, 3, -3, -8. And that's it. We've kind of culled out the important information from that system, and now we're going to manipulate this matrix. So there are what are called elementary transformations to a matrix. There are 3 things that you can do to this matrix that will preserve the solutions to the original system. The first thing that we could do is we're allowed to interchange 2 rows. If you interchange 2 rows, it's not going to change the solution set. Another thing that we're allowed to do is multiply any row by a constant, and it should be a non-zero constant. Okay, so that's the second thing we're allowed to do. The third thing that we're allowed to do that's pretty powerful is we can add 1 row to another. So why the heck would we even want to do these things? Our purpose is to be able to manipulate this matrix in a series of steps that will get to another matrix where we can really easily read off the solutions to this whole system. And these are the 3 tools that we have. And we're going to go through a long example. But these are the 3 operations that you can do to a matrix that won't change the solutions. We definitely don't want to change the solutions as we're going through the process of Gauss-Jordan elimination. We just want to make it easier to see it. As I go through this process, a little bit of notation. I'm going to call row 1 R1, row 2 R2, and row 3 R3. And my goal right now is to get a diagonal of 1s all along here, just to be 1s, with 0s below and above. Seems like a weird goal, but this is actually going to really help us find the solution to the system. So before I even write anything down, knowing that this is my goal, what is a way that I could get this 2 to become a 0? Well, these are the only things I'm allowed to do. 2 and 3 are really what you're going to use mostly. I could multiply row 1 by a -2 all the way through, and then add it to row 2. That would create a 0 right here. That's what I'm going to do. So I'm actually going to keep row 1 as it is, and so we'll just rewrite row 1. Because row 1 has the entry in the diagonal that I want. So that'll be 1, -2, 4, 12. Now, I am going to think about multiplying row 1 by -2 and adding it to row 2. And I'm going to do both of those things in one step. So let's see. -2 times 1 plus 2 gives me 0. And then -2 times -2 plus a -1 will give me 3. And then we have -2 times 4, that's -8, plus 5, and that is a -3. And then we have -2 times 12, that's -24, plus a positive 18, so that is -6. I've got my new second row. Awesome! And the great thing is I have a 0 right here, just like I wanted. Okay, I'd also really like to get a 0 here, and this one's even a little simpler. What if we just add row 1 to row 3 and put the new solution in row 3? This would create a 0 right here. So that's what we're going to do, just add row 1 to row 3. So row 3 to that gets added row 1. So row 1 is like the workhorse. It's enabling us to get these zeros. Okay, 1 plus -1 is 0, -2 plus 3 is 1, 4 plus -3 is 1, 12 plus -8 is 4. Good! We have a good start. Okay, I've got the zeros I want. The next step I'm going to do, I really want this to be 1, so I'm just going to multiply this whole row through by 1/3. So I'm allowed to do this because of this guy right here. So 1/3 times row 2, and row 1 I keep the same, but row 2 now becomes 0, 1/3, -1/3, sorry, not 1/3, what am I thinking? 3 times a third is 1, -3 times a third is -1, and -6 times a third is -2. This is my new row 2, and I'm just going to keep row 3 as it is. It had a nice 1 at the beginning of it. So I'm really starting to get my diagonals of 1. I've got my zeros below. I need to get this to be a 0. That's my next step, is this guy right here. I'm going to attack that. So what if I took negative row 2 and added it to row 3? Then this would become a 0. I'm going to keep row 2 as it was, and but I am going to be thinking about multiplying -1 times row 2 and adding it to row 3. That's our new row 3. Okay, so -1 times 0 is 0, plus 0 is still 0. We'll make that a black 0. Okay, and then -1 times 1 is -1. Plus 1 is 0. That's the 0 that we want. And then -1 times -1 is positive 1. Add that to 1, and we get a 2. -1 times -2 is 2. Add that to 4, and we get a 6 right here. In this same step, I would like this -2 to be a 0 because I need zeros below and above our line of diagonal ones. So to create a 0 here, I'm going to take 2 times that second row and add it to the first row. Then we would get a 2 here, add it to this, and we'll have a 0. So we'll take row 1 plus 2 row 2, and we'll put that as our new row 1. So 2 times 0 is 0 plus 1 is 1. And 2 times 1 is 2. Add that to negative 2, and we get the 0 that we want. 2 times negative 1 is negative 2 plus 4 will become 2. And 2 times negative 2 is negative 4 plus 12. Negative 4 plus 12 is going to be 8. And we have a new row 1. Things are looking good. I've got some zeros where I want them. Next thing I'm going to do is I want to make this guy right here a 1. So I'm going to multiply row 3 by 1/2, which I can do by this rule. I went ahead and multiplied that 1/2 through row 3, and this is what I got. We're definitely getting closer to being done. I want some zeros here, though. And so I'm going to take row 3 and add it to row 2 to get a 0 right here. So when I add 1 to negative 1, wait, I guess we better start over here. When I add 0 to 0, I get 0. 0 to 1, I'm going to get 1. So I get 0, 1. They stay the same. And then when I add 1 to negative 1, I'm going to get the 0 that I want. We can't stop there. We got to keep adding, though. So when I add 3 to negative 2, let's see, that would be a 1. I'm going to also, while I'm at it, try to get rid of this guy right here. And I would need a negative 2 times row 3 so that I could have a negative 2 right here to add to this. So negative 2 times row 3, and we'll add that to row 1. So row 1 plus a negative 2 times row 3. And if I do that, I'm going to have 0 plus 1 is 1, 0 plus 0 is 0. So those first two entries on row 1 don't change. And then the real magic happens where I'm going to take negative 2 times row 3, so negative 2 right here, and add it to row 1, and that's going to create the 0 that I want. But of course I have to do it to the last entry too. So negative 2 times 3 is negative 6. And then I'm going to add that to the 8. Negative 6 plus 8 is 2. Okay. So good news, guys. We just achieved our goal. We have a diagonal of 1s with zeros below and above. Now the next thing I'm going to do is I'm going to retranslate this. I'm going to put this back into equations. So write this matrix as my original equations. And the first row says 1 times x1 plus 0x2 plus 0x3 equals 2. My next row says 0x1 plus 1x2 plus 0x3 equals 1. So the second line says x2 equals 1. And the third row says 0x1 plus 0x2 plus 1x3. So x3 equals 3. You can see why we wanted to put it in this form, because the answer just pops out. And so we have it. This is our solution to the system, and we can write it. This is great. This is our solution. And we can write it as an ordered triplet also. So 2, 1, 3. Let's do a quick check and make sure that really is a solution to this system. So 2 minus 2 is 0. 4 times 3 is 12. That worked. 2 times 2 is 4. Minus 1 is 3, plus 5 times 3, 15. 3 plus 15 is 18, that's right. Negative 2 plus 3 is 1, minus 9. 1 minus 9 is negative 8. Yeah, it's definitely a solution. So I want to make a couple of comments about these elementary transformations. They I want to make a couple comments about these elementary transformations. They change how the matrix looks, but they do preserve the original solutions. So this system of equations, the solutions to this system don't change through these elementary transformations. And why do we do it? Why do we even go through this whole big long honkin' process? Is because once we get to the end, it's much easier to read off the solutions to the system. It's impossible to look at this and say what the solutions are. But once you transform it into this form, then it's easy to read off the solutions. Okay, a little bit of matrix notation. Say we have a matrix. This is actually the one from the last example. You can talk about the sizes of a matrix, and it's always the number of rows by the number of columns. So this matrix in particular is a 3x4 matrix. And then sometimes we need to talk about a particular entry, and so we need some notation for that. A lot of times you'll see Aij, and this is the element in the ith row, jth column. So for example, if I want to know in this matrix what the A23 entry is, I go to the second row, third column, 1, 2, 3, and so A23 is 5. If I was wondering what the A32 entry was, I would go to the third row, second column, and the A32 entry is 3. Sometimes you'll see this, I think the textbook might write it as, they'll say the 2-3 entry. And when they use this notation, it can be a little confusing because you think of this as an ordered pair or a point on a plane. But when they use this whole phrase, the 2-3 entry, then we know that we're talking about something like this. So even this, the 2-3 entry would be 5. And the 3-2 entry would equal 3. One particularly important matrix is the identity matrix. It's a square matrix, so an n by n matrix, where you have, that's the size of it, where you have ones along the diagonal and zeros everywhere else. And it can be size 2 by 2, 3 by 3, 4 by 4, all the way up to whatever. This is the identity matrix. For our last example, we're going to look at a case, it's a 2 by 2 case, but all of the coefficients, it's actually a series of systems, and all the coefficients are the same, but the constant terms are different. And you can solve multiple systems at the same time if the coefficients are the same in one sort of big long matrix, and we'll take a look at that. So this time we're going to solve this system here, x plus y equals b1, 2x plus 3y equals b2, but our constant terms are going to change. We have 3 different options, and we're actually going to solve for all of these in one matrix. So first we'll put the coefficients of the variables into a matrix, and then we're actually going to put all possible solutions just at the end of the matrix. This doesn't happen very often, but you may see this, so I wanted to go through an example. So my goal is to get ones on this diagonal and a 0 here and a 0 here. Everything on this side are just the constant terms. So this is where we want our diagonal of 1s. And I start by taking R2 times negative 2R1, and that's going to create a 0 here. You can go through and see. And the other step that I needed was to create a 0 here. So I took a negative R2 and added it to row 1, and I created what I wanted. Now each of these are solutions to each of the corresponding problems. So this will be the solution if what we started with for constant terms was this. This will be the solution if what we started with for constant terms was this. And this will be the solution if we had started with this for constant terms. This is just really like smushing 3 different systems of equations into one matrix. The only advantage to doing this is you only have to do these row operations one time for the whole series of 3 systems. Like I say, this is rare, but it does come up in the homework, so I wanted to touch on it. Our big ideas for today were we talked about what a matrix was, the 3 important elementary row operations, and we did go through solving a system of equations. We'll get lots more practice with that, but at least we have a start.